All right, let's jump right into this explainer. Today, we're unpacking a really incredible mathematical framework that was designed specifically to conquer those brutal computational bottlenecks we run into with complex engineering designs. I mean, if you've ever found yourself just sitting there, waiting days, or let's be honest, sometimes weeks, for a single high-fidelity simulation to finish running, then you know exactly the pain point we're tackling today. We're looking at a brand new paper from the journal Optimization and Engineering, and it essentially completely rethinks how we allocate our computational budgets.
So, this is the big question driving our analysis. As engineers, as data scientists, we're constantly trying to scale up high-fidelity simulations, right? But we all know that standard surrogate models just hit a brick wall when the dimensions get too high, or when the cost per evaluation gets too extreme. So how do we actually move beyond those limitations without burning through our entire resource allocation on just a couple of design iterations?
Here is our roadmap for today. We're going to cover 5 main areas. First, the computational bottleneck. Second, multi-fidelity Bayesian optimization and validation costs. Third, the consequential improvement, or CI function. Fourth, the Gaussian process modeling framework. And finally, the benchmark validation findings.
Okay, let's kick things off with sections 1 and 2, diving into the computational bottleneck and how MFBO handles validation costs.
This setup brilliantly illustrates the core problem we're facing. On one hand, you have your high-fidelity evaluations. Think of these as your physical prototypes or your massive, fine-mesh, finite-element simulations. They're super expensive, but inherently trustworthy. On the other hand, you have low-fidelity evaluations. Sure, they're cheaper and way faster, but they're obviously less accurate. Now here is the catch that almost everyone misses. Existing methods treat these low-fidelity samples as standalone events. They completely ignore what we call the hidden deferred cost. Think about it. In real engineering, if an algorithm suggests a great design based on a cheap, low-fidelity run, you still have to run a high-fidelity simulation to validate it before you can actually build the thing.
So, the crucial takeaway here is that by ignoring that hidden cost, traditional methods like max-value entropy search or knowledge gradient are basically wasting your budget by oversampling cheap data. They literally treat high and low fidelity like they are the exact same type of information, just with different price tags. But the proposed consequential improvement, or CI approach, it throws that outdated logic right out the window. It explicitly factors in the strict engineering reality that any actual real-world improvement must be validated. Which brings us nicely to Section 3, the Consequential Improvement, or CI function itself.
Enter consequential improvement. By formalizing this concept, the model actively prioritizes actual, validated improvements over cheap theoretical ones. It's a completely novel acquisition function that selects your next design solution and the fidelity level at the exact same time. How? By weighing the anticipated improvement directly against the total, real-world cost it's actually going to take to prove that improvement is legit.
Let's look at how the math actually shakes out. It's pretty clever. If the algorithm is evaluating a high-fidelity selection, it just looks at the anticipated improvement and divides it by the cost of this current iteration. Pretty straightforward, right? But if it's considering a low-fidelity selection, it calculates the quotient of the anticipated improvement divided by the cost of the current iteration plus the cost of the subsequent high-fidelity validation iteration. To stop uncertainty from compounding, this really elegant formulation penalizes the low-fidelity option precisely by the cost of the future iteration required to validate it.
Moving right along to Section 4, the Gaussian process modeling framework. To make this all work, the authors utilize a highly efficient, hierarchical, multi-fidelity Gaussian process. The real magic here, which they describe as recursive information fusion, is that this method completely eliminates the need for cross-fidelity correlation coefficients. Instead of trying to estimate how every single fidelity level correlates with every other level, which, let's face it, is a total computational nightmare, the model recursively builds predictions based on all evaluations at or below the current level. It's incredibly streamlined.
This creates a double-loop searching process that ensures every single decision perfectly balances exploration against your strict computational budget. Basically, you update your hyperparameters, maximize the CI function to pick your next move, run the simulation, deduct the cost from your budget, and repeat. And crucially, look at step 4. The loop strictly concludes with a final sample at the high-fidelity level. No matter what, it guarantees a validated result.
All right, let's hit our final section. Section 5, Benchmark Validation Findings. Let's see how this actually performs.
The researchers didn't just test this on one nice, easy niche problem. They put consequential improvement through the ringer across 5 distinct analytical environments, scaling all the way from simple one-dimensional functions up to a complex 8-dimensional borehole design. Plus, they systematically manipulated the cost ratios, from low to medium to high, to mimic different real-world scenarios, like comparing a rapid math calculation against a massive time-consuming fluid dynamics simulation.
Now, let's be real about the trade-offs here, because they are clear. Max Value Entropy Search, MES, has the lowest CPU time for the surrogate model itself, but as we discussed, it struggles heavily with oversampling low-fidelity data, which just wastes your overall budget. The new CI method does require more CPU time. It's about 2.2 times slower than Knowledge Gradient because it has to temporarily update the surrogate to evaluate those hidden future validation costs. However, it offers completely unmatched stability and completely avoids redundant low-fidelity sampling. Basically, it trades a tiny bit of CPU time upfront for massive savings in your actual simulation budget.
But the true test is when you apply CI to high-dimensional, finite element analysis. The researchers pushed this algorithm to its absolute limits using structural engineering benchmarks, specifically a 25-bar spatial truss and this massive, highly constrained 200-bar planar truss. This 200-bar truss features 77 nodes, 29 specific member groups, and applies strict penalties for stress and displacement violations across a bunch of different loading scenarios. This is as real-world as it gets.
And the results are incredible. In these complex engineering simulations, the CI method decisively outperforms traditional optimization methods. It consistently hits the most rapid convergence, showing this awesome, swift initial decline before hitting an early, incredibly stable plateau. By completely sidestepping that trap of oversampling at low-fidelity levels, it literally makes every single simulation count. When they restricted it to a strict 40 evaluation budget, it left standard quasi-Newton and genetic algorithm baselines entirely in the dust. So, synthesizing all this benchmark data, what's the big takeaway for you? Well, if you are dealing with high-dimensional design spaces or scenarios with huge cost disparities between your high and low-fidelity simulations, or, really importantly, environments where a final physical prototype or high-fidelity validation is absolutely mandatory, these are the exact scenarios where data scientists and structural engineers should immediately drop standard MSEs or KG algorithms and swap in the consequential improvement function.
Considering the massive, often totally crippling cost of finite element analysis and multi-scale simulations, it is really worth taking a hard look at your current workflow today. Are you currently ignoring the deferred cost of validation? Ask yourself how implementing this mathematically rigorous approach could eliminate those hidden validation costs and maximize the efficiency of every single computational dollar spent in your own lab.